We have learnt about electric fields and magnetic fields in isolation, where an electric field is a region in space in which an electric charge experiences a force. It has the symbol uppercase letter E, it's measured in newtons per coulomb, and electric field lines are always drawn or directed from the positive charge towards the negative charge. And magnetic fields are something completely separate to that, where they are a region in space in which a ferromagnetic material will experience a force with the symbol letter B, and measured in Tesla, where magnetic field lines are always drawn directed from the north pole to the south pole of a magnet. What is important to realize is that these two fields are actually two sides of the same coin, and that coin is called electromagnetism, where electromagnetism essentially explains the idea that the electric and magnetic field are related to each other in a very simple way, and that way is that when you have a changing electric field, so we use the Greek letter delta here to show that we have a changing electric field, that will automatically produce a magnetic field perpendicular to it. And that relation goes both ways, where a changing magnetic field would in turn produce an electric field. Creating a changing field is very simple, as a changing electric field simply means a charge that is moving, and we know that when charge is moving, we know that we have a current that is moving through a wire or some kind of conductor. So essentially what we are saying here is that a changing electric field, which is a result of a current, or a current that is a result of a changing electric field, will always induce a magnetic field, and this is known as the motor effect. Conversely, a changing magnetic field, which basically means when you have a magnet that has a magnetic field around it and you move that magnet, that will automatically create a changing magnetic field that will in turn create an electric field, which can obviously then go on to produce a current, and this is known as electromagnetic induction. So once again, electric and magnetic fields are seen as two sides of the same coin, where a changing electric field in the form of a current can produce a magnetic field that can be used to create mechanical energy or movement, and the converse of that being that a changing magnetic field in the form of a moving magnet can create an electric field, which can in turn induce a current, which is known as electromagnetic induction. In this section on electromagnetism, we always deal with conventional current, which we know is the flow of positive charge from the positive terminal of a battery to the negative terminal of a battery. And so we know that when we have a current carrying conductor, what that means is that there is an electric field that is set up across that conductor as a result of the poles on either side, and as a result we have charge moving through that battery or moving through that conductor. As a result of the moving charge, we have a changing electric field, which we know through electromagnetism that a changing electric field will always induce a magnetic field that is perpendicular to it. This is always true of current carrying conductors, that there will always be a magnetic field produced that is perpendicular to the direction in which current is flowing through a current carrying conductor. The way that we show this is we show or represent a current carrying conductor that is carrying current, in this case out of the board, so that is from the table upwards. We show it with a dot, and what we would show is that there's a magnetic field that is produced that is perpendicular to it, and we demonstrate that with 3 concentric circles, and we determine the direction of the magnetic field around that current carrying wire using the right hand wire rule, which says that we point our thumb in the direction of the current. In this case, the current is coming out of the board or towards the camera, and our fingers will curl in the direction of the magnetic field, which tells us that the magnetic field is rotating counterclockwise around this wire. We would then also demonstrate or notate a wire that is carrying current into the board with a cross. And once again, we know that since that is carrying current, it has a changing electric field, which in turn produces a magnetic field that is perpendicular to it. We show that with 3 concentric circles to represent the magnetic field. And using the right-hand wire rule, we point our thumb in the direction of the current and our fingers curl in the direction of the magnetic field around that wire. So once again, this is based on the idea that an electric current creates a changing electric field, which results in a magnetic field produced perpendicular to the current in that wire. And we can determine the direction of the magnetic field around any current carrying conductor using the right-hand wire rule, which says that if we point our thumb in the direction of the current, our fingers curl in the direction of the magnetic field. A solenoid is any wire that is wound into a coil, and so we can use this to create an electromagnet by starting with a current carrying wire that we have over here that we wrap around an iron core. And so our current carrying wire carrying current in this direction that we have over here. As we can see, it wraps around the back, which is represented by the dotted line, comes around the front and carries the current in that direction. Now we know that any current carrying conductor has a magnetic field produced perpendicular to it that acts in concentric circles around it, and we can determine the direction of that magnetic field using our right-hand wire rule, which says here that the current is going into the page or into the board. Using our right-hand wire rule, we can see that the current or the magnetic field is directed as follows for around the wires at the top of the solenoid. And for the wires at the bottom, using our right-hand rule, once again, we can see that the magnetic field moves or is directed in this direction for the wires at the bottom of the solenoid. Now what we can see here is that we have in various places around the solenoid, we have opposing magnetic fields. We can very clearly see that the magnetic field in the center or in between these wires is uniform and in the same direction, as all of those lines point in the same direction. But what we can see is that between these wires we have opposing magnetic fields, which means that the resultant magnetic field there would be 0. And then finally we can see that around the outside of these wires we have once again a uniform magnetic field. What this does is it allows us to draw a magnetic field around the solenoid that looks almost identical or is identical to the magnetic field that would be produced around a magnet, and we can even determine the direction of those magnetic field lines. We also remember that magnetic field lines are always directed from the north pole of a magnet to the south pole of a magnet. And what we've done here is by using a current carrying conductor and using the fact that a changing electric field in that current produces a magnetic field, we have created an electromagnet using a current carrying wire. We can use what is called the right-hand solenoid rule to determine which is the north pole of a solenoid by curling our fingers in the direction in which the conventional current flows. As we can see, the conventional current flows along the top of the solenoid upwards here, and then our thumb would point in the direction of the north pole of that solenoid. Obviously, if I were to put my hands on the back of the solenoid, my fingers would curl downward, and once again my thumb would point to the north pole. So we can then determine the polarity of the solenoid without having to draw the magnetic field around that solenoid. So there are 3 factors that affect the strength of the magnetic field of an electromagnet. The first one being the number of turns. Obviously, if you put more turns around, there are more interfering magnetic fields, which creates a stronger net magnetic field. Obviously, a bigger current would produce a greater strength magnetic field around each wire, which once again would strengthen the electromagnet. And then obviously, if you had a different type of core, obviously something that magnetizes more easily or maintains its magnetism for longer, you would increase the strength of that electromagnet. The motor effect is the phenomenon whereby a current carrying conductor placed in a permanent external magnetic field experiences a magnetic force. And we know that a magnetic field, or the magnetic field lines, are always directed from north to south. And so we can draw those in, and we can illustrate the motor effect by showing that a current carrying conductor that is carrying current out of the board, which is obviously illustrated with a dot that represents conventional current moving out of the board, we know would have a magnetic field surrounding it because of the changing electric field within that conductor. As a result, we have a magnetic field surrounding it and perpendicular to it, and we can determine the direction of that magnetic field using the right-hand wire rule, which tells us that the magnetic field is directed in a counterclockwise direction around that current carrying conductor. And now what we can see is that beneath this wire we can see that the external magnetic field interferes constructively with the magnetic field surrounding the wire, which results in a stronger magnetic field below the wire, because we know those both magnetic fields acting in the same direction would result in a stronger magnetic field. And at the same time, above the wire, we can see that the magnetic field around the wire is in the opposite direction to that of the external magnet, and as a result, there is no resultant magnetic field below the wire. Now, what we can see here is that when there is a very strong magnetic field beneath the wire and no magnetic field above it, we would create a force that exists upward on that wire that is sometimes referred to as the Lorentz force. Now, we can also use Fleming's left-hand motor rule to determine this direction. The left-hand motor rule is used with our fingers placed perpendicular to each other, where our thumb represents the force, our index finger represents the magnetic field, and our middle finger represents the current. And so what we can do is we can point our index finger in the direction of the magnetic field, our middle finger in the direction of the current, and our thumb shows us that the force on this conductor is then upwards. It can then be seen that a conductor that is carrying current into the board would experience a force downward, and this is, as you can see, why it is called the motor effect, because what we have is, if these two are one and the same conductor, one carrying current into the board and one carrying current out of the board, we would create a turning motion, which is the principle on which all electric motors operate. Electromagnetic induction is the phenomenon whereby a changing magnetic flux induces an EMF, and this would always start with an external magnetic field, which, as we know, is always directed from the north pole of the magnet to the south pole of the magnet, and a conductor that does not have a current passing through it. So what we have here is essentially a wire that is running into the board that is not carrying a current yet. Now, in order to create a changing magnetic flux, we need that wire to move, and that is only made possible by exerting a force on it. So in this case, we are starting by exerting a force on this conductor, and as a result of that force, the conductor moves, which means that it moves through this external magnetic field, and as a result, there's a changing magnetic field, which creates, in essence, or it can be thought of as a magnetic field around this conductor. Now, we can use the right-hand wire rule, which says that if we curl our fingers in the direction of the magnetic field, our thumb will point in the direction of the current. And what this then tells us is that by moving this wire upward in this external magnetic field, we are inducing a current that runs into the board in this conductor. Now, it is not necessary to draw a diagram like this every time, because we can use the right-hand dynamo rule. The right-hand dynamo rule says that if you point your index finger in the direction of the external magnetic field and you point your thumb in the direction of the force, so if we say we want to apply a force downward on this object. So we point our index finger in the direction of the magnetic field and we point our thumb in the direction of the force. Then our middle finger will indicate the direction of the induced current in that conductor. And so what we can see here is that by us applying the external force here, meaning we rotate this coil, we can induce a current within that coil. This is the principle upon which all generators, also known as dynamos, operate, because what we are doing here is we are converting from mechanical energy, the energy of movement, into electrical energy, obviously, that is created in that. A side-by-side comparison is the easiest way to understand the theory around motors and generators, where we know that motors operate on the motor effect and generators operate on the principle of electromagnetic induction. And motors convert electrical energy into mechanical energy, whereas generators convert mechanical energy into electrical energy. We know that for motors we would always use our left hand to determine the direction of the force being exerted on a current carrying conductor, and in generators we would use our right hand to find the direction of the current induced in a conductor. There are, generally speaking, two types of generators, those being alternating current and direct current, and only one type of motor, that being the direct current motor. Important to note that both the direct current motor and the direct current generator both use a split ring commutator. In the motor, it converts direct current in the external circuit into alternating current in the internal circuit, that being the coil in the magnetic field. And in the DC generator, the split ring converts alternating current in the internal circuit in the coil into direct current in the external circuit. Whereas in an AC generator, we use slip rings, which transfers the alternating current in the internal circuit into alternating current in the external circuit. The output for an alternating current generator shows the oscillation from 0 to a maximum induced EMF, back to 0, back to or down to a minimum induced EMF, and the output for a DC generator shows that the induced EMF oscillates from 0 to a maximum, back to 0, back to a positive maximum without going to a negative maximum. In these generators, the induced EMF is directly proportional to the speed of the rotation. The frequency is also directly proportional to the speed of the rotation, meaning that if the generator were to be rotated faster, the frequency and the induced EMF would increase. And the induced EMF is also directly proportional to the number of turns in the generator, or number of coils, and also directly proportional to the magnetic field strength. And then finally, the output from a DC motor would be that the rotation speed is directly proportional to the current, directly proportional to the number of coils, and directly proportional to the magnetic field strength. A common question that comes up would be how to convert an AC generator into a DC motor, and that is done by replacing the slip rings with split rings and adding a DC power source. The Walter Pent simulation of a direct current motor shows us how the motor effect is used to convert electrical energy into mechanical energy. We can see that this starts with a source of direct current, most often a battery, which forces current to flow from the positive terminal to the negative terminal. We can see that it is a direct current source because the current maintains the same direction throughout. We can then see that the coil that is placed within the external magnetic field, also referred to as the internal circuit, is connected to this external circuit by means of a split ring and carbon brushes. The carbon brushes are used to maintain contact between the internal and external circuit while there is rotation taking place. And as we can see, the purpose of the split ring is to convert the direct current in the external circuit into alternating current in the internal circuit. We can see that by following one side of the coil as it rotates around within this external magnetic field, and we see that every 180 degrees the current in that coil changes direction. We can see that that is a result of the split ring, which converts direct current in the external circuit into alternating current in the internal circuit. The Walter Fent simulation of a generator shows how electromagnetic induction is used to convert mechanical energy into electrical energy. And we can see that with this setup here, that shows that there is some external force that is rotating this coil within the magnetic field. Now, whether that is a hydroelectric power plant or a normal coal-fired power plant or a wind turbine, it is something external that is causing this coil to rotate within this magnetic field that we have here. As we can see, when the coil moves through that magnetic field, there's a change in magnetic flux which induces a current within that coil. We can see here as well, by following one side of the coil, that the current in that coil changes direction every 180 degrees. And so we use a split ring commutator to convert the alternating current in the internal circuit in the coil into direct current in the external circuit. As we can see here, the current in the external circuit is constantly flowing in the same direction. So we say that the split ring commutator converts alternating current in the internal circuit into direct current in the external circuit by means of a split ring commutator and carbon brushes. We can see that the induced EMF ranges from a maximum to 0 back to a maximum, but does not change direction because this is a direct current generator. We can then replace the split ring commutator with a slip ring that then allows the alternating current in the internal circuit, which has not changed, to be converted into alternating current in the external circuit. It does that by maintaining contact with a certain side of that coil and allowing the carbon brushes to maintain that contact as it rotates. So once again, what we have here is we have alternating current in the internal circuit, which is now converted into alternating current in the external circuit, and we can see that here by seeing that the current ranges from 0 to a maximum, back to 0, and then changes direction to a negative maximum before returning to 0.